DevOps and CI-CD Part 15. This episode has 4 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. What is Podman? Here's a strong way to approach it. What is Podman? Podman, Pod Manager, is an open-source container engine used to develop, run, and manage OC-compliant containers. It is often considered a Docker alternative because it provides a very similar CLI experience but does not require a central daemon. Developed by Red Hat, Podman is widely used in enterprise Linux environments. Key difference: Docker versus Podman. Docker CLI Docker daemon. Dockered containers. Podman CLI containers. Podman is daemonless, meaning there is no long-running Dockered process. Features: daemonless architecture, run containers directly without a background daemon. Benefits: reduced attack surface, simpler architecture, better security, rootless containers. Podman supports rootless execution by default. Podman run Ginks containers can run as a normal user without root privileges. OC compliant. Podman works with OC standards and runtimes such as runt. Cron images built with Docker generally work with Podman and vice versa. Docker compatible commands. Docker run Ginks. Podman run Ginks. Most Docker commands work with minimal or no changes. What is a pod in Podman? Unlike Docker, Podman supports pods natively. A pod is a group of containers sharing network namespace, IPC namespace, storage resources. Example: pod application container, sidecar container similar to a Kubernetes pod. Pod example: create a pod. Podman pod create. Name my pod. Run container in pod. Podman run DT. Pod my pod. Ginks generate Kubernetes YAML. Useful feature: Podman generate Kuba. My pod produces Kubernetes manifests that can be deployed to a Kubernetes cluster. Podman versus Docker feature: Podman Docker daemon. No. Yes. Rootless support. Native supported but optional. OC compatible. Yes. Pods native. No. Docker CLI compatibility. High. Native security generally stronger by default. Good. Common commands: run container. Podman run dean Ginks list containers. Podman ps pull image. Podman pull Ginks build image. Podman build. My app interview answer: 7+ years experience. Podman is an open-source, OC-compliant container engine developed by Red Hat. Unlike Docker, Podman uses a daemonless architecture, where containers are managed directly without a central daemon process. It provides strong support for rootless containers, improving security by reducing the need for privileged operations. Podman is largely compatible with Docker commands and additionally supports Kubernetes-style pods natively. Due to its security model, OC compliance, and Kubernetes integration capabilities, Podman is a popular choice in enterprise Linux and cloud-native environments. Nice. Let's continue. Question 2. Explain container life cycle. Here's a strong way to approach it. Container life cycle. The container life cycle describes the different states a container goes through from creation to deletion. Life cycle stages: image created, running, paused, unpaused, stopped, removed. 1. Image. A container starts from an image. Example: Docker pull Ginks. The image acts as a template for creating containers. 2. Created container metadata and file system are created, but the application is not started. Docker create. Name web Ginks. Check status. Docker PSA output. Created. 3. Running container process is actively running. Docker start web or Docker run dean Ginks state. Running. 4. Paused container processes are temporarily suspended. Docker pause web resume. Docker unpause web use case. Maintenance, troubleshooting, resource management. 5. Stopped. Exited main process inside the container has stopped. Docker stop web or application exits naturally. State. Exited container still exists and can be restarted. 6. Restarted. A stopped container can be started again. Docker restart web or Docker start web. 7. Removed container is permanently deleted. Docker rm web after removal. Container metadata is deleted. Writable layer is deleted. Attached volumes remain unless explicitly removed. Common life cycle commands: action command create, Docker create, run start, Docker start, stop, Docker stop, restart, Docker restart, pause, Docker pause, unpause, remove, Docker rm list, running, Docker ps list all, Docker psa container state. Example: check container status. Docker inspect web, look for state. The exact commands and code are in the written question bank. Great. Moving on. Question 3. What is image immutability? Here's a strong way to approach it. What is image immutability? Image immutability means that once a container image is built and tagged, it should never be modified. If changes are required, A new image is built and deployed instead of updating the existing image concept. Immutable approach. Version 1 image change required. Build version 2 image deploy new image not. Version 1 image modify existing image cross mark deploy. Why is image immutability important? 1. Consistency. The same image runs everywhere. Development, testing, production, all environments use the exact same image. 2. Predictability. If an image works in testing, the same image will work in production. My app. v1. 2. 0. The contents never change. 3. Easy rollbacks. v1.0 v1.1 v1.2 issue found. Rollback to v1.1. Simply deploy the previous image. Version 4. Better security. Easier vulnerability tracking. Easier auditing. Prevents unauthorized modifications. Example. Build image. Docker build t my app. v1. Deploy. Docker run my app. v1. Later. Application changes. Docker build t my app. v2. Deploy. Docker run my app. v2. Never modify my app. v1. Immutability in CI/CD code. Commit build image tag image push registry. Deploy. Every build generates a new immutable artifact. Example tags. My app. 1. 0. 0 my app. 1. 0. 1 my app. 1. 1. 0. Avoid using latest bad. My app. Latest reason. Tag contents may change. Difficult to reproduce. Deployments. Preferred. My app. 1. 4. 2 my app. 20,260,530 my app. A 1B2C3D. Often teams use git commit hashes. My app. 8F3C2D1 Kubernetes and immutability deployment. Image. My app. 1. 4. 2 new release. Image. My app. 1. 4. 3 Kubernetes performs a rolling update using the new immutable image. Benefits. Checkmark. Consistent deployments. Checkmark. Easier rollbacks. Checkmark. Better auditability. Checkmark. Improved security. Checkmark. Reproducible environments. Checkmark. Reliable CI/CD pipelines. Interview answer. 7+ years experience. Image immutability is the principle that a container image, once built and published, should never be modified. Any change to the application, configuration, or dependencies requires building a new image with a new version tag. This ensures consistency across environments, simplifies rollbacks, improves traceability, and supports secure, reproducible deployments. In modern DevOps and Kubernetes environments, immutable images are a core best practice and are typically versioned using semantic versions, build numbers, or git commit hashes rather than mutable tags like latest. Alright, next question. Question 4. Explain distroless images. Here's a strong way to approach it. What are distroless images? Distroless images are minimal container images that contain only the application and its runtime dependencies, without a full Linux distribution. They typically exclude shell, bash, sh, package managers, apt, yum, debugging tools, unnecessary system utilities. Traditional image versus distroless image. Traditional image application runtime shell package manager system utilities libraries. Distroless image application runtime required libraries. Everything else is removed. Why use distroless images? 1. Smaller attack surface. Fewer binaries mean fewer vulnerabilities. No bash, no apt, no yum, no curl. Attackers have fewer tools available if a container is compromised. 2. Improved security. Example. Traditional image. Docker execute container bash. Distroless image. Bash not found. Interactive shell access is typically unavailable. 3. Smaller image size. Example. Ubuntu-based app. 200 MB plus distroless app. 30 to 50 MB benefits. Faster downloads, faster deployments, reduced storage costs. Example. Docker file. Traditional. From Append 21 copy AppJar CMD Java, jar, AppJar, distroless. From GCRIO or distroless or Java 21 copy AppJar CMD AppJar. Multi-stage build with distroless common pattern. From Maven 3.9 Eclipse Temurin 21 as builder copy. Run MVN package from GCRIO or distroless or Java 21 copy. From equals builder target or AppJar CMD AppJar. Build tools stay in the builder image and do not end up in production. Popular distroless images maintained by Google. Distroless project examples. Distroless or static distroless or base distroless or Java 21 distroless or not edges distroless or Python 3 challenges. Debugging. No shell, Docker execute app bash fails. Instead, use logs, use sidecar or debug containers, use Kubernetes ephemeral containers. Learning curve. Teams accustomed to shell-based debugging may need new operational practices. Distroless versus Alpine feature. Distroless Alpine Shell available. No yes. Package Manager no yes. Attack surface smaller small. Debugging harder easier. Security higher high. Image size very small small. Best use cases check mark. Production applications check mark. Microservices check mark. Kubernetes workloads check mark. Security focused environments check mark. CI or CD pipelines following least privilege principles. Interview answer 7+ years experience. Distroless images are minimal container images that contain only the application and the runtime dependencies required to execute it, without including a full Linux distribution, shell, package manager, or debugging utilities. By removing unnecessary components, distroless images significantly reduce image size and attack surface, improving security and deployment efficiency. They are commonly used in production Kubernetes environments and are often combined with multi-stage Docker builds to separate build time dependencies from runtime artifacts. The primary trade-off is reduced debugging capability, which typically requires alternative troubleshooting approaches such as logs, sidecar containers, or ephemeral debug containers. Let's keep going. That wraps up this episode. Nice work practicing, and see you in the next one.